I'm Sean Carroll from Caltech, and I picked an intentionally boring title for my talk because what I want to actually say is quite non-boring, and a lot of people will be disagreeing with it. The official title is Fluctuations in de Sitter space. The unofficial title is Fluctuations in de Sitter space, Quantum Fluctuations in de Sitter space do not happen. And this is work I did with two very talented young graduate students, Kim Boddy and Jason Pollock at Caltech. Don't blame them if you disagree with me for any of the work in here. If you like the work, then you can give them all the credit. So I think the place to start is by thinking about classical statistical fluctuations, what we think of as thermal fluctuations in ordinary stat mech. So let me try to distinguish something that has bugged me for many, many years. What is the difference between a thermal fluctuation and a quantum fluctuation? Thermal fluctuations, of course, can exist in perfectly classical statistical mechanics. So, in fact, I want to undo the name thermal fluctuations and simply rename them Boltzmann fluctuations, because you don't need to be in a thermal state or in thermal equilibrium or anything like that. All you need is the general Boltzmann setup that you have macro states and micro states. So you have some space of states which have microscopic dynamics, which is perfectly unitary, but then you chunk it up into macro states that look similar. You have a macro state, which is described by its temperature and pressure, which is essentially static. The macro state in equilibrium is not evolving, it's just sitting there. Nevertheless, we believe after Boltzmann that there can be fluctuations into lower entropy states, and that there's an explanation for why. That's because hidden beneath the macro state is the micro state, which is really evolving in time. The thermal state is macroscopically static, but the microscopic state is time dependent, and therefore if you plot entropy versus time, you will get occasional fluctuations downward in entropy. This is true, everyone believes it. We tell similar stories about quantum mechanics, but sometimes we tell them when we shouldn't. So I'm going to examine quantum mechanics in the Everett approach, the many worlds interpretation. I'll mention what happens in other approaches later. In fact, what happens in other approaches is very, very different. So it's one of the rare cases where your interpretation of quantum mechanics really matters. So think about a harmonic oscillator in a ground state, or think about any quantum system in an energy eigenstate. So you have a wave function that is spread out, and there's a phase that is oscillating around. But what I'm going to say is that a quantum system in an energy eigenstate is static. Now, of course, there is time dependence because of this phase, but in an energy eigenstate, there's just one overall phase that has no effect whatsoever on anything observable. One way to see that is to say that all the same information is contained in the density operator, and that is strictly, manifestly time independent. So something that's in an energy eigenstate is not changing with time. And that's a physically meaningful statement. There is no statement you could make about the quantum state in an energy eigenstate that would be true at one time and not true at another time. This is pretty obvious, so I'm going to keep saying it because you'll want to agree with me later. There's nothing changing, nothing going on in this quantum state. I would ask for people to just wait until the talk is over. I need to put in a whole bunch of stuff, and then we'll talk about it. I need to get through a lot. In case you're wondering whether quantum states really exist, here's a photograph of one that came out a couple months ago. This is an electron in one of its energy eigenstates in a hydrogen atom that they actually experimentally detected. And my point is that this is not a blurry picture of a little ball called the electron that is actually orbiting. This is the quantum state. This is what actually the physics is, and it's not changing with time. It's perfectly static. So therefore, in quantum mechanics, unlike classical mechanics, even thermal states are static. In the classical case, there was secret time dependence because there was a microstate. In quantum mechanics, a thermal state is described by a density matrix, which is diagonal in the energy eigenbasis. So that's a generalization of being an energy eigenstate, but it's a generalization which retains the idea that this is perfectly time independent. This density matrix tells you everything you need to know about the quantum state in this thermal mixed state, and there is no time dependence. There's no question you can ask about this thermal state which would be true at one moment in time and untrue at another moment in time. Therefore, in that sense, quantum mechanics is less fluctuation-y than classical mechanics. You can have a perfectly thermal state which will never fluctuate in quantum mechanics. And yet, we're always talking about quantum fluctuations. In that simple harmonic oscillator, we always talk about 0-point fluctuations, vacuum fluctuations, quantum fluctuations. Why do we do that if you believe the story that the state is not actually evolving in time? Well, we do that because we have observables in quantum mechanics. The real difference between classical mechanics and quantum mechanics is that observables are much more important. They have a much more subtle nature in quantum mechanics. So the variance of a typical observable whose eigenstate you are not in will be greater than 0, which means if you observe something like the position of the harmonic oscillator over time, you will get different answers even if it's in its ground state. You will see it jitter around. That's where the fluctuations come in. But, and here's where things get a little bit controversial, I'm going to claim that observables only matter when things are being observed, and they don't matter when things are not being observed. That sounds pretty anodyne, but in fact that's where all the controversy will arise. So what do we mean in the Everett interpretation by something being observed, an observation happening? It requires decoherence. The wave function of the universe needs to branch. So you start in a very specific kind of state. There's an apparatus, which is in its ready state, that is going to do the observing. There's a system, which can be whatever it wants. That's not very specific. There's an environment, which is large and low entropy, into which we can dump all of the information we're eventually going to trace over. And these three factors start unentangled with each other. They do not start in a generic state. If you want your apparatus to correctly measure what it is you're looking for, the apparatus interacts with the system and becomes entangled. The up part of the spin gets entangled with the up reading on the apparatus, and likewise the down. And then we have decoherence. The apparatus, emits photons, or the atoms in the environment bump into it. It becomes entangled with the environment. And these two environment states are generically going to be either orthogonal or very, very close to it. So we have two different branches of the wave function that no longer talk to each other. So in this sense, what we mean by quantum fluctuations are the time dependence of the readout of the apparatus as you do this procedure over and over again. You could do this and you get sort of a plus, for example. Then you reset the system to what it was and you read it again. And on a random branch in the wave function of the universe, the readout of the apparatus will be some sequence of time-dependent answers, plus, minus, plus, 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 minus, minus, etc. That is a quantum fluctuation, but it requires all of this stuff. It requires a ready state, it requires no initial entanglement, and so on. It is not going to happen if the whole state started in an energy eigenstate. This time dependence would not appear. You can put a little bit of formal math onto these words. You can use the decoherent histories formalism to ask, starting in some density matrix and ending in the same density matrix, when is it the case that in between there is a truly dynamical process that represents some sort of fluctuation? I don't care what kind of fluctuation it is. A Boltzmann brane could appear, whatever kind of fluctuation you're interested in. You construct a projection operator onto states that look like the kind of fluctuation you're asking about. And then the other projection operator is everything that doesn't look like that. And you ask, after delta T1, did you actually fluctuate into that? And then did you evolve back? So the question is not, if I put this projector onto the state, is the amplitude non-zero? That can very often be true, but it does not represent a truly dynamical happening. If that amplitude, if that branch is not decohered from the rest of the state, it is not a truly dynamical process that in some sense happened. So when this really does happen is when the decoherence functional vanishes. And I'm not going to dwell on the math here, but there's math. I need to put the math on there. So you calculate this functional of the possibility that it fluctuated and didn't fluctuate. I guess the other words for the non-experts here, think of the two-slit experiment. This is what you are always told to do when people talk about the decoherent histories program. Ask, did the electron go through one slit or the other? And if there's no decoherence in between, the answer is it did not go through one slit or the other in any sensible way. Only if the decoherence functional vanishes can you assign a probability to going through one possibility or the other. So here's the decoherence functional, and you can just use energy eigenstates to write it as a sum over a whole bunch of oscillating things over time. So if you're in a finite dimensional Hilbert space, you have a finite sum here. You have these things with sort of generic random looking phases, and therefore if you wait long enough, these are going to add up to 0. If you wait long enough, if the dimensionality is finite, these will vanish, and you will in fact say, yes, I did dynamically fluctuate into a Boltzmann brane or what have you. But that's only starting with a generic initial density matrix. If you start with a static initial density matrix, then these coefficients look like delta ij. The ei minus eij's vanish, and you just get a sum of a whole bunch of constants. This is a fancy way of saying that if you're in a time-independent state, nothing fluctuates, nothing changes with time. The possibility of having a Boltzmann brain or not having a Boltzmann brain do not decohere with each other. It's not a truly dynamical process that happens. So let's apply this to de Sitter space. Again, sorry for the people who are not experts in de Sitter space in the room. You're not going to become an expert after this talk, but de Sitter space is a cosmological solution to Einstein's equations, a very simple vacuum solution that has nothing but a cosmological constant in it and has a positive cosmological constant. So there's a positive vacuum energy, there's an accelerated expansion. Geometrically, it kind of looks like a hyperboloid. There's a Hubble parameter, an expansion rate, that is also constant in time. And long ago, we have done quantum field theory in de Sitter space. One of our participants was a major player in this game. There's a global vacuum state called the Bunch-Davis vacuum. You can, Gibbons and Hawking back in the 1970s showed that if you're in de Sitter space in the vacuum, there's a very close relationship to what happens around a black hole, namely that even the vacuum is a thermal state with a non-zero temperature. And what does that mean operationally? If you put a particle detector in the vacuum, it will see particles. There is no state in de Sitter space in which the particle detector never sees any particles. So it has a temperature. You can sort of take the horizon-sized region in de Sitter space and say, well, I can never interact with anything outside the horizon, so let me just trace over all that stuff. And even though the global state is a pure quantum state, in each horizon you get a thermal density matrix. It has a entropy given by 1 over the cosmological constant. It is described by a finite dimensional Hilbert space. The dimension is very big for hour of actual value of the cosmological constant, but it's still not infinite. So you might say, well, but what if I'm not in the vacuum state? Well, I happen to have a theorem in my pocket that says eventually you will be in the vacuum state. If you're doing QFT in de Sitter space, we're not talking yet about quantum gravity, there is the cosmic no-hair theorem, classically proven by Bob Wald back in the 1980s, and now there are quantum field theory generalizations of it. So here's another geometrical way of representing de Sitter space. The whole of de Sitter space is this square. This red triangle is the region that is observable by one observer. So imagine the observer is just on the boundary here. And despite the fact that it's tilting, this is a horizon where things are moving at the speed of light, the physical size of this region is actually constant. So this line is 1 Hubble distance across, so is this line, so is that line, and so forth. And the cosmic no-hair theorem that says unless you have enough stuff in the universe that you just collapse to a singularity, if you wait long enough, all the excitations and stuff other than the vacuum energy leave the horizon, and you approach asymptotically and relatively quickly the Bunch-Davis vacuum. So put all you like in there. Put some observers, put a solar system, put 100 billion galaxies, wait long enough, a Google years or so, and we will, in our real world, be in the Bunch-Davis vacuum in de Sitter space. So there's a conventional wisdom, and I say this because I have promulgated this conventional wisdom for years now, about what happens in the de Sitter patch, in this vacuum state that is a thermal state. Well, it has a finite entropy and a finite temperature. There are therefore fluctuations, says the conventional wisdom, into lower entropy states with a certain rate that is exponentially suppressed by the size of the fluctuation. This can be either good or bad, depending on what your goals are. It could be bad because you could fluctuate into real conscious observers, Boltzmann brains or Boltzmann Earths or Boltzmann galaxies or Boltzmann universes or what have you. This is bad because if you live in a universe where almost all examples of people exactly like you are freak random thermal fluctuations rather than nice people who politely came into existence through evolution after the Big Bang, then those observers have no right to believe any of their beliefs about the world. They just randomly fluctuated into their brain. So this whole cosmology would be cognitively unstable, and most cosmologists think we should reject models where this is the case. It's not a universal consensus, but most people think that. So that can be bad. Looking at me. It can also be good. You might want to have a landscape of vacuum states where there's many, many different vacuums. I drew 2 of them here. There's 10 to the 1,000 that I didn't draw. But you might want to start in one and populate all of the others. So you can say, well, because of these fluctuations, even though if I'm in this true vacuum, even though this false vacuum is higher energy and lower entropy, Eventually, I will fluctuate upward into it. And Anthony Aguirre and I, with Matt Johnson, wrote a paper about that. So the role of these fluctuations into lower entropy states in landscape multiverse cosmology is absolutely crucial. And what I want to say is that everything on this slide is wrong. I no longer believe it. Why? Well, you can fill in the blanks by now. The density matrix in a horizon patch of de Sitter, once you get rid of all your excitations, is the Bunch-Davies vacuum. It's the density matrix that you get by tracing out outside the horizon this thermal state. It is diagonal in the energy eigenbasis in the static Hamiltonian. It is therefore static. Nothing happens. Whatever is true at one moment of time in this vacuum state is also true at every other moment of time. So if there's no Boltzmann brane there now, there will not be a Boltzmann brane there tomorrow. You could see Boltzmann branes pop into existence if you were there looking, but you are not there looking. Nobody is there looking. There is no out of equilibrium macroscopic measuring apparatus that is constantly observing and interacting with the vacuum. There is just the vacuum. Therefore, there are no fluctuations. Therefore, you do not produce Boltzmann branes. You do not create a whole bunch of observers just like us. You also do not fluctuate upward to higher energy vacua via uptunneling. Now, this story that I told you, just because it's on fairly firm grounding when I use this language, was in the context of quantum field theory in curved spacetime. We know pretty well, or many of us are convinced, that that's not the whole story in quantum gravity. So we need to include the idea of horizon complementarity. So when you include quantum gravity, you take that entropy seriously as the number of states, and you try to ask, well, so how do I think about the actual number of degrees of freedom within the horizon patch? Is it all of the degrees of freedom, or is it just some subset of a larger system? And this is a loophole that I think will actually get you out of what I said, but only in cases we don't think are realistic. So horizon complementarity says that if the true vacuum is de Sitter, that is to say, if there's no other vacuum somewhere else in the theory you're working with, then the total Hilbert space will be finite dimensional. And in that case, you don't have the cosmic no-hair theorem. If you have a finite dimensional Hilbert space, then there's the Poincare recurrence theorem, the quantum version, and it still holds true. It's a theorem. So even though you might look like you're very, very close to a thermal state, you're never actually there. You are actually always time dependent, and all of the conventional wisdom about fluctuating into Boltzmann branes, other vacuum states, etc., would still be true. But if there's somewhere in your theory is a Minkowski vacuum state, that means that the real Hilbert space of your theory is infinite dimensional. That means that you can, in fact, relax. There is no theorem that says you need to bounce back. In the branch of the wave function, which has support on the false vacuum that you are in, the state will look static. There will be no fluctuations. You will never fluctuate into Boltzmann branes or anything like that. So this is what most people think is the realistic case. If you're a string theorist, you believe that at least there's a 10-dimensional Minkowski vacuum. The real Hilbert space is infinite dimensional, and therefore I claim that in the string theory landscape, there's no Boltzmann brane problem. I've also assumed the Everett formulation of quantum mechanics. I'm thinking that the quantum state is the physical thing. There's no sort of hidden variable underneath. If there is a hidden variable underneath, which many people believe, then of course that can be fluctuating around, just like the microstate fluctuates around in Boltzmann's story. So in hidden variable models, nothing that I said is valid or interesting. Likewise, in dynamical collapse models. So you have a model, I don't think we have dynamical collapse models which apply to quantum field theory in curved spacetime or quantum gravity, but if somehow you insisted that there was a new law of nature that said the wave function stochastically changed every so often, then that would obviously be time dependence, and that would obviously allow for all the sort of fluctuations that I said were not there. Now the looming question for all the sensible cosmologists in the room is, what about inflation? We love inflation, and we're always talking about quantum fluctuations in the context of inflation. Have you just undone all of those decades of work? So no, I have not really. The story that we tell in inflation about the production of density fluctuations goes through absolutely unchanged, because the production of density fluctuations happens in a time-dependent way. The important time dependence is not during inflation. During inflation, you are quasi-exponential. It's pretty close to static. You're not producing any entropy. But there's a quantum state that is more or less static, and then you reheat. Inflation ends. At reheating, you produce a buttload of entropy, and that is like an observation. Then you collapse the wave function of all those different fluctuations, and you realize different patterns of perturbations on the sky like we see in the cosmic microwave background. So there's nothing that this story has changed about the story that we tell ourselves about density fluctuations and inflation. the story that some subset of us tell ourselves about eternal inflation might need to be dramatically changed. And I'm being a little bit more wishy-washy here because the problem is harder, so I'm going to try to get the place where my ground is the firmest settled first. In slow roll eternal inflation, you're never in a static state. The field is slowly rolling. You're slowly rolling down a potential. But the story we tell ourselves is that in addition to the classical motion of the field, there are quantum fluctuations back and forth in the potential. And in fact, the story we tell ourselves is that you can model these quantum fluctuations as a stochastic field variable that sometimes fluctuates down but sometimes fluctuates up. If it fluctuates up often enough, those regions will dominate the volume of the universe and inflation will be eternal. What I'm saying, the whole moral of my story, is that quantum variables are not like classical stochastic variables, so that way of talking to ourselves has been wrong all these years. So because what I think physically happens here is that you settle into a quasi-static state where it's true that there's time dependence, but there's not entropy generation. There's not branching of the wave function during inflation. I think what happens is a single quantum state rolls down the hill. I do not think there's any sense in which there are stochastic fluctuations up the hill. So at the very least, I'm skeptical of that story, and I think we should analyze it more closely. So this is the motto you should take home. Quantum variables are not like classical stochastic variables. In a static state, there are no real quantum fluctuations unless you look at it. That has important implications for Boltzmann brains, up-tunneling. Even though inflationary perturbations are fine, eternal inflation might need to be rethought. Thank you.